This is the last lecture of the course. This is on shared memory and forking. This is in the system building skill. This is the system building skill for week 10. So one of the things that we have not yet discussed is that how can we actually communicate between two processes. We know how we can do that between two threads. We actually saw an example that because these threads are lightweight processes, they have some kind of a shared section of memory where any variable that is part of that section, for example the global variables, can then be accessed by all the threads within the process, right? So this way you can have an implicit communication between the threads. So global variables, we used I think a global variable in one of the example programs to communicate between the two threads. But how about two processes? Threads, as we all know, are lightweight processes, and they share certain resources. But what if there are two different processes? Is there a way to somehow communicate from one to another? Apparently there are ways, right? And the simplest way to do that is using something known as a common memory block or a shared memory. Okay, so within the main memory, a part of the main memory can be reserved as a kind of shared memory. That shared memory is accessible to pretty much everyone, right? And how does it happen? Really what happens is, the operating system has its own ways to check whether a particular process, whatever memory area it is trying to access, whether that access is authorized or not. Okay, if the access is unauthorized, the operating system blocks that access. This is what happens in general. But with this shared memory, okay, any process is allowed to read or write this process. And this is the issue as well, that it could be done by any process. So just to imagine what really happens is, each process has its own memory space. So if p2 tries to read this part, it will be an invalid access to memory. Similarly, if p1 tries to access, let us say, this part, it is an invalid memory access. So the operating system will block this access and this will not be allowed. But if you create a separate memory, a memory block within the main memory, and the operating system basically says, okay, I'm going to allow anyone who wishes to read or write to this memory, then this becomes a kind of shared memory. So the only thing, the only thing that you have to understand is that this shared memory is not really a part of any of these processes. It's an independent memory block, and this block can be accessed by, let us say, any process which has a key. Okay, a key is basically a kind of you can say it's an identifier in order to point to this particular memory location. So this is an identifier that the operating system provides you, and with the help of this, any process that has this particular identifier can, of course, go and access this memory location. So this is the idea. If I want to write to this shared memory, if I want to write some data, all I need is the key associated with the shared memory. And then let us say if there is another process which wants to have a communication with this process can then read this data written in this shared memory. However, the problem really here is that there is no check as such. Check as in, any process that has access to this memory key can go and access this shared memory. So there is really no way to restrict it to only, let us say, P2 and disallow P3 and P4. So the only access control is done using this memory key. So that has to be kept like a tightly, like a tight secret. How do I do that? This is the problem. Not only that, there could be issues known as synchronization issues. Synchronization as in, there is really no check that two different processes are not writing simultaneously in the same memory location. Okay, so this has to be done by you. You have to do it on your own. The protocol to access this memory, that has to be implemented by you. But yeah, a shared memory is created, and then it is basically attached to one or more processes, and then these one or more processes can communicate via this shared memory. The typical flow that is followed, we'll have a look at some code as well, but the typical flow is something like this. There is a function called shm get, this SHM get function needs to be given a key, and this key is basically the actual access identifier for the shared memory. So when you give this function the key that you want to be associated with the shared memory, along with some flags. Okay, these flags are basically it involves what kind of access control do you want. There are a number of things that you can do, but there is a specific flag for creating a process, IPC underscore create. If you use that flag, this SSM get is going to create a new shared memory and then return you it returns you the access mechanism to access this. But before you understand how to access it, there is a function called ftok. So this function can be used for you, only used by you to generate a key. Okay, so you understand that basically the most important part here is that this key has to be exactly the same whenever it is used by any of the communicating processes. So how do you manage that? How do you make sure that this key is exactly the same? So this ftok function can be used for it. It takes a path, basically a char asterisk type, and then a number, and then it turns it into a key. Okay, and then this key can be used to create the shared memory. So why is this important? So you can then say that you are going to derive a key out of two aspects that you can basically pass on. So you can say the string, the pass string, you can say, is abcd, and the pass number is 15. Okay, so any process that knows these two pieces of information, abcd and 15, can then go on and access the shared memory. So with the help of ftok, you can create a key and then you pass it to shm get. Shm get essentially creates whatever is required. The portion within the memory, it gets created, but this does not give the process directly an access to that particular memory location. You still have to attach this process to this shared memory, and to do that there is a function called shmat. Okay, so whenever a process calls shmat, it now gets attached as in now the operating system knows that this process is trying to access this particular memory location. This the the returned pointer, so this call will return a pointer, is the actual pointer that you can use in order to use the shared memory. So the type of this pointer is actually void asterisk, so you can then typecast it to whatever form you want. For example, if you want to use this memory if you want to use this memory as a place to store strings, you can typecast it to char asterisk. If you want to use it to store integers, you can typecast it to int asterisk. So because this is a void asterisk pointer, it is just a block of memory. You can use it any way you want. Okay, you can typecast it any way you want. You can typecast it into types of structure variables or objects, whatever you want. Okay, if yeah, usually when we create the memory, we have to provide the size for it, and this size is basically in bytes. So whatever number of bytes you have allocated, you can use it whatever way you want. And once everything has been done, once the tasks that you were trying to achieve have been done, then you should detach yourself from the memory using the shmdt call. And then finally the memory could be marked for deletion. You have to understand that you do not simply delete this memory, you actually mark it for deletion, and then you let the operating system decide what is the best time to delete this memory segment. But by flagging it using this shmctl function, you can actually tell the operating system that okay, now there is no requirement for this shared memory, so please mark it for deletion. As soon as all the processes that have attached themselves to this memory, they end. At that point of time, operating system can take a call when to when to delete this shared memory. Okay, we'll have a look at some code, but there's one last thing that is left now. So we saw how a new thread of execution can be created from an older thread, let us say the main thread, using the POSIX APIs, right? But and we also know that the major difference between a thread and a process is that threads can share data. Now it might seem to be a positive aspect most of the time because you have access to a common area. Sometimes you do not want that. Let us say from the security perspective, you want two threads to be completely independent of each other. The copies of variables, for example, that they have, including the global variables, should be different. It might be in certain situations you might want to have such a thing. So in such case, it is better not to create a thread, but to create a new process. Okay, the actual idea is exactly the same. You still the conceptual aspect of this whole scenario is still the same. You are going to create a new thread of execution. It's just that this new thread of execution is also a new process. Okay, it's not an actual thread, it's a new process. And this can be done using a call to the fork system call. So if I hope most of you at least remember what a system call is. We heard this term when we were discussing the Linux kernel. So this is a system call fork, but you have an access to do so via a function of the same name, and you can do that in your C++ code. So this fork system call creates a new a single new process, not a thread, a single new process. And multiple calls to fork will actually create multiple new processes, similar to how we created threads, right? And there is again, similar to the thread part, there is a parent and child relationship between the calling process and the newly created process. And this new process, by the way, is a replica of its parent. So you remember during threads we passed a function pointer, right? That I said, where will the new thread of execution start executing, right? So I said that you can pass a function pointer and the new thread will start executing. It will start executing statements from that particular function. But here, when you call a fork, what really happens is that a replica of the parent's code as well as the parent's data segment, that is created. So the new process is ideally a copy of the old process. There's just one difference. Okay, this fork call, whatever you made, its return type, it returns a value, by the way, and that value can be stored, and this value is going to be different in the newly created process and the older process. And this single value can then be used to do a bifurcation. So how something like this, let us say, I do it like this. I say PID equal to fork. Now at this point of time here, uh, two copies of this particular process are now created, right? So the code from here onwards is executed twice in two different processes. Okay, but and everything remains the same. If there are any local variables, global variables here, they all remain exactly the same in both the processes. The only thing that changes is this value PID. So if you check this PID's value, by the way, if it is less than 0, then it means that the fork failed. If it is greater than 0 but not equal to 0, then it is essentially the case. So if it is greater than 0 but not 0, then this is basically the parent process, the process which called the fork. Okay, so this piece of code, this cout statement, is executed in the older process. Okay, the process that called the fork. And this PID is double equal to 0. So this value, wherever the return value is 0, this is the newly created process. So now you can understand that this value, this PID, can be used to do a bifurcation. Otherwise, what is the point of creating a new process, right? If they have the exact same replica of code, why do you want two processes, right? You would like to do something else in the new process, and that something else can be done by just using this PID's value. If the PID's value is 0, you are sure that this is the newly created process, and if PID is a non-zero positive value, then it is the parent process. In fact, in the parent process, the value that is returned is actually the process ID of the newly created child. Okay, so this bifurcation can be used in order to write two different types of code. So let us now have a look at some code. So here the first thing maybe I can show you is the fork itself. Let us say I am doing something like this. So this is at this point I am making a fork. It is just creating a kind of family tree here, right? And there is the parent process, the process that starts the whole thing is the L1, the level 1 process. It has some PID, some process ID. Then there is a call to fork. So what will happen from here onwards, right? So this if statement, it gets executed, and then a forked value comes in. So the value will come and sit here, right? That is the idea, that the value, whatever is the return value of fork, that will come and sit here, and from there onwards there is a bifurcation. Okay, as soon as the fork returns, there is a bifurcation. There are two different processes which will execute this code, and this if statement will be executed by both the processes. And and what does it say? If not fork, so it means that the value that is returned by fork, if it is not 0, then I should have also put a check for the case where the fork failed, but yeah, for now just assume that the fork will go through. So here what will happen is, in the child process, the returned value of fork will be 0, and in the parent process it will be a non-zero positive value. So from here onwards there is a bifurcation. This if part, you will enter this if part only in the parent, and in the child you will enter the else part. That is the difference. Similarly, again within the parent you make another fork, right? And this cout is executed by the parent. Actually this parent is essentially the L2 process. That is the idea. And in fact, okay, I maybe uh, yeah, I think yes, that is out. So basically this, now from here onwards you have an L3 process. So there are two level 2 processes, there are two level 3 processes. This is the idea, that at one point of time you are going to make a call to fork, and then from here onwards there are going to be multiple processes. The only way you can differentiate between them is the returned value of fork. So let me just execute this for you. Let me just put it into a file. Okay, so here there are some PIDs, okay, process IDs. So this is the first process, the process that was created by the process that was created by me in the first case. And then from there onwards you can see that there are some processes, right? The first L2 process has the PID 10100. So this is the first process, which is basically the parent of everyone, the level 1 process. Then I have two level 2 processes, and their PIDs are 100 and 10101, right? And then there are, I think, four level 3 processes. So why? Because the second fork is being executed in both the processes. Okay, so that is the idea. With the help of a fork you can create a complete tree of processes, right? So the second fork gets executed in both the processes. So now you have basically a hierarchy of processes, because the first fork made a bifurcation. Now the second fork in both made, even more bifurcations, so on and so forth. So this is the idea that sorry so this is the idea that at level 2 you have these two processes. Okay, at level 3 you have these four processes. So the idea is that fork can be used to create a complete family tree of these processes, and this tree can get really complicated, and it's exponential in nature. So please use fork in a way that you understand, so that you make sure whatever you are trying to do it is done exactly in the same fashion. So this is for the fork. And for the shared memory, I've just created two programs. This is the first program. Basically this program is the writer program. This is going to write some data in a shared memory. So you can see what am I doing. I'm basically using a string as a shared passcode and a number, and then I'm using this FTOK to generate a key. Now this is guaranteed to generate the same key as long as these two inputs, they are the same, right? So with the help of this, you can, so as long as any process knows both these things, it this process can generate a key out of it. So that is exactly what I'm doing here. I'm just generating a key out of these two constants, and then I'm using the shm get. Here I am using this flag IPC underscore create. This will mean that please create the shared memory for me. This is only done once. After that, whenever I want to use this memory, I can just I do not need this create flag. And so this returns an ID for an identifier for this shared memory. One, and if if by the way it does not, if the shared memory creation failed, you will receive a 0 in the ID. So it has to be a non-zero value, a positive non-zero value. So once you do know that the shared memory has been created, then from there onwards the next step is to attach this process with the created shared memory. So to do that, you pass the shared memory's ID. There are some other things that you don't need to know here as of now. Just know that this is how you attach a process to this memory location. And then you can use, and by the way, the return type of this is void asterisk. So now it's up to you how you want to interpret this. So here when I created the shared memory, I give the size of the shared memory as the size of data, and data is basically a long, so this will be a what 8 bytes thing on most of the systems. So here you have this 8-byte memory, and you are going to interpret it as a long pointer. So from here onwards, you can use this memory pointer like this, as if it's any other memory location pointer. So I'm just doing value at memory pointer equal to data, and then I say I wrote this data. Okay, so and then after that I'm going to delete, I'm going to detach myself from that particular shared memory. Okay, so I think I made a mistake there. I guess that has to be, no, it's fine, that is fine. Okay, so so then the next thing that you have to do is check out this code here. I still need these two passcodes, the string as well as the number, and then I'll call the key. So at this stage, the key should be exactly the same in both the in both the processes. Okay, so this is the second process. It will generate the exact same key that it wants. With the help of this key, it can then retrieve the SHM ID, the shared memory ID, and here you can see I am not giving the IPC create because I am assuming that the memory was created by the previous process. And then this is the boilerplate stuff. Here again the same thing I have to do. I have to attach this memory, I have to attach this process to this memory. Once I have the pointer, I can use this pointer to read the data. So here I am just doing data equal to @ memory pointer, and then towards the end I am just saying that now I am done. Please, this is how you delete using the SHM CTL. Okay, IPC RM ID. So this is a very brief overview of how the shared memories things work. You can try it here. So you say run me first. It says I'm going to create a shared memory now, and I wrote this data. This was a different process, by the way. And now you say uh, then run me 2, and this 42 has been read from that shared memory that we just created. And after reading this, the shared memory was also marked for deletion. Okay, so this is a very brief overview of shared memories and fork. I hope you guys can run this code and have a look. Okay, there is some homework, you can check it out as well. Thank you, bye.